Welcome to the next video in the real analysis video series, and here we are solving the problem that we left off, which is to get the bounds on this set taken from various different number sets. And so I still haven't checked whether Zorich it puts 0 in the natural numbers or not, but if we assume that 1 is the least natural number, then the only natural number lower bound you could possibly give for this set is the number 1. You have more options for the upper bound. You could have chosen 10 or 11 or infinitely many others. Okay, let's take them from the integers. Certainly 0 is in the integers, and that is a lower bound. So there's a distinct lower bound, this time taken from the integers. We could take an integer equal to 20 for the upper bound if we wanted to. And for a rational lower bound, we could have chosen a half or -1, lots of other options. An upper bound, again, many options. 10.1 is an acceptable rational number option. Let's move on to the definition now of a maximum and a minimum. So if we take a non-empty set of numbers and if we let R be some number, then if R is an upper bound and an element of the set, then in that particular case, we call R the maximum of X. We use this notation max X to denote the maximum. Likewise, we define a minimum with similar notation and so on, so that there are your definitions of the maximum of a set and the minimum of a set. We'll get straight into an exercise. Let X be a non-empty finite set of numbers. Prove that X always has a maximum and a minimum. I guess there's a little bit of a giveaway in that it seems like the proof is kind of long. I don't know, maybe I put a note in here that isn't really part of the proof, so maybe it's not quite as long as that indicates, but maybe be a little ready for a possibly surprisingly long proof to this. After all, if you think about it, right, if you want a hint, right, okay, pause the video right now if you don't want a hint and you'd like to think about this completely fresh. But if you'd like a hint, it's coming in a second. I want to give you time to pause the video if you want it, but okay, here it goes. You know, this may not be the easiest thing to prove completely directly, and so since set, right, every finite set has some number of elements, then it might be a good idea to do induction on the number of elements in X.